So welcome everyone to the next seminar. I'm delighted to introduce Victoria Wagner. He's from the Technical University of Munich. So Victoria is an experimental particle physicist who has a particular focus on what she's going to be telling us today about coherent elastic neutrino-nucleus scattering. So she really got her PhD from Heidelberg before doing postdocs at the CEA in Saclay. And then now in at TUM. So she's been working on experiments neutrino experiments measuring this coherent elastic neutrino-nucleus scattering process, which is something that I know several people in the audience are particularly interested in from the theory side and the experimental side. So yeah, I thought it would be a great topic to have a seminar about. So thank you for waking up so early to give us this, Victoria, and why don't you take it away?
Okay, thank you very much for this very kind introduction and for inviting me to give the seminar. So, as said before, today I was asked to give a seminar on coherent elastic neutrino-nucleus scattering, but from an experimentalist's point of view. So I will try to give you an overview of the field and with a special focus on where it's going and what the experimental challenges are that we are facing and how we are facing them. Okay, so let me briefly review coherent elastic neutrino-nucleus scattering, or shortly CEvNS. So it's a process which is well predicted within the standard model. And as the name suggests, so a neutrino scatters off elastically a nucleus. And that nucleus gets a nuclear recoil, which is our experimental signature. This process is coherent as long as the momentum transfer is small. So in that case, the neutrino cannot resolve the structure of the nucleus, and it interacts coherently with the nucleons. Typically, this is the case for momenta smaller than the inverse of the size of the nucleus. And that is, so for medium-sized targets, about 30 MeV. So here on the slide, I hope you can see my cursor, is the approximated cross-section with respect to our observable. We have a few contributions. So we have the weak charge that depends, of course, on the target nucleus. Then we have some kinematics that are mainly given by the detector itself or mainly by the neutrino source, so which neutrino energies are available. And then we have the weak form factor. And the weak form factor describes the distribution of the weak charge in the nucleus. And it's 1 if the momentum transfer is 0. And then the larger the momentum transfer gets, more and more deviates from 1, so it gets smaller than 1. Then the weak charge, due to the structure of the neutral current, the distribution from protons is suppressed, so we are left with mainly a dependence of the cross-section on the number of neutrons squared. And so here on the right, you see the cross-section as a function of the neutrino energy, only up to 10 MeV, so we assume that we are in the full coherent regime. And the cross-section scales with the number of neutrons squared and the square of the initial neutrino energy. So we see it here for different target nuclei, and for heavy target nuclei such as tungsten, the CEvNS cross-section can be up to 3 orders of magnitude larger than IBD, so inverse beta decay, which is the classical neutrino detection channel. And we can also see that there's no thresholds for CEvNS. So other than IBD, with CEvNS, we can also study neutrinos with energies smaller than 1.8 MeV. And the last thing I want to mention about CEvNS here is that it does not distinguish the different or the known neutrino flavors. So it's a flavor blind process. And all of this makes CEvNS the dominant neutrino scattering process for neutrino energy smaller than 50 MeV. Okay, so we all see that we have this large boost in neutrino in the neutrino cross-section. So we can use it to do physics with it. And there are several things that I would like to highlight here. So first of all, it's a standard model process. So we can use it to do a precision test of the standard model, meaning we can probe this n-square dependence. We can measure the Weinberg angle at low momentum transfer. But we can also look for deviations from the standard model. So we can look for physics beyond. And here specifically, we can test new neutrino interactions, new mediators, new couplings of neutrinos. We can probe the electromagnetic properties of the neutrinos. So we can especially search for magnetic dipole moments of the neutrino. And since it's flavor blind, it's also a new channel to search for stereo neutrinos. So the sources that we use here, they need to have a very high flux because it's still a neutrino interaction. And typically we use here, so man-made sources or reactor neutrinos or neutrinos produced in pion-decays at rest. I will come to the details of those sources later. And then in the future, one can also think about using radioactive sources such as chromium. Typically these experiments, we want to have a very high flux of neutrinos, so we want to go very close to a reactor or to the neutrinos beam source. So that puts a lot of demands on the experiments themselves. So they are typically located at shallow sites, which means that we have a lot of background, and they need to be small. I mean, you cannot put a huge ton scale detector next to a nuclear reactor. So, so here we are talking about small neutrino experiments, typically kilogram or even gram size. And they all feature low thresholds, low detector thresholds, so of keV or even sub keV. And this is what my talk will focus on. Just to mention it, there is of course more. So I mentioned the weak form factors, which of course includes a lot of nuclear physics. So this can also be probed in CEvNS, especially here. So CEvNS is one nice way to probe neutron form factors, neutron RMS radii, etc. And then what I also like a lot is that we can do, once we measured the CEvNS cross-section, we can use CEvNS to study neutrino sources. So we can use it to do solar physics and supernova physics. Here, we typically need a large exposure, so we need large detectors that are deep underground. And you already see, this is like using a dark matter detector, and we will see also that later. Okay, so let me start with the neutrino sources that we use nowadays to study neutrino properties. Reactor electron anti-neutrinos are produced in the beta decays of the fission products. And so here in gray, you see the reactor neutrino spectrum. It sharply falls towards 1 MeV. So we're talking about low energy neutrinos, which means that we can assume to be in the fully coherent regime. And then reactors, they provide a very high flux of neutrinos. The other source are beam neutrinos, which are produced in pion plus decays. So we get a prompt muon neutrino that is monoenergetic, around 30 MeV. And then when the muon decays, we get a spectrum of anti-muon neutrinos and electron neutrinos that reaches up to 53 MeV. Typically, these beams provide a lower flux than reactors. And since the energies are so high, we already start to come into the regime where we are not fully coherent. So this all sounded very, very negative for beam neutrinos, but actually they're great. And so this is what. So let's have a look at the key experimental challenges. So the key challenges are to reach these low thresholds. So we want to measure nuclear recoils, and we need a low background. So here on this plot, you see the maximum recoil energy as a function of the neutrino energy. For different target nuclei, so here the dotted line is silicon, so an example for a very light target. And then the solid line is tungsten, which is a very heavy target. And we see that for 30 MeV neutrinos, we are fine with having rather high thresholds, so of a few keV. Then if we go to the reactor neutrinos, so if we want to measure 3 MeV neutrinos, we need to go to sub-keV thresholds. So here the maximum, so the dependence of the maximum recoil energy is very steep. And so, I mean, it falls steeply here, and this is a logarithmic scale. Then for the background, so there is, though CEvNS has a high cross-section, it's still low for neutrino standards. So we're talking about 1 CEvNS events in a few days. Of course, this depends really on the experiment, but this just to give you an idea. And that means our background needs to be lower than that. So for beam neutrinos, I'd say this is rather easy because those beams are pulsed, so you have a timing information and you know when to expect a neutrino event. For reactor neutrinos, we don't have that. So many experiments, they rely on comparing reactor off versus reactor on data, meaning they search for an excess in the data when the reactor was running over the data where the reactor was shut down. But that is not enough. So those experiments are, since they are typically close to the surface, they need a very good shielding against ambient background. And I will show you some examples. Anyway, those two requirements, so low threshold and low background, are the same requirements as for dark matter searches. So there's a large overlap between these two fields, technology-wise. Okay, so on this slide, I'd like to show you that CEvNS is a very active field. So there are many experiments all over the world, which are already running or which are being built, both for using reactor neutrinos and beam neutrinos. And so I'd like to start with a coherent experiment that is the only experiment so far that observed CEvNS. So coherent is located at the spallation neutron source in Oak Ridge. So it's a stopped pion-decay addressed source, and they're using 3 different detectors with 4 different detectors with 4 different targets. So that is cesium iodine, argon, germanium, and sodium iodine. Here in this plot, you see the expected nuclear recoil spectra for the different targets. And I'd like to highlight here, so in yellow, you see cesium iodine, which is already being decommissioned. And we'll come to that in a minute. That had a threshold of like 6 keV. And then argon, which is lighter than cesium iodine. So this is shown here in this in orange. It has, so the spectrum is lower. So here we see the n-square dependence, and the spectrum is much more stretched out compared to cesium iodine. So it's because, yeah, so the heavier the target, the more the nuclear recoil signal is suppressed. Okay, so Coherent did the first. There's an echo. Okay, so Coherent did the first observation of CEvNS on cesium iodine. They took more than 3 years of data, and so their final result is that they observe CEvNS with more than 11 sigma, and they determine the flux average cross section. So flux average cross section means that they average the cross section over the neutrino spectrum provided by the source. And so the measured cross-section is compatible within 1 sigma with the standard model prediction. And here you see the first publication in July 2017, of the first observation of CEvNS. Okay, so by measuring the cross-section, they can also measure the weak mixing angle at low momentum transfer. And but they can do more. So they can also look for additional or new couplings of neutrinos to quarks. So here you see additional couplings or the limits on additional couplings to the U and the D quark. And what is also very nice, so they can probe if the CEvNS cross section is flavor dependent, and since they have the timing information. So this is what they do here. So here you see the electron cross section versus the muon cross section, and that's compatible with the standard model. Then Coherent also measured the cross section, so the CEvNS cross section on argon with more than 3 sigma. So here you see the spectrum. And so what is extremely nice, so now we have 2 measurements of the CEvNS cross section. So on argon, so a light target, and on cesium iodine, a heavy target. So this plot shows the cross section as a function of the neutron number. And you can see that it follows the expected n-square dependence, taking into account the form factor. So the green line here is one calculation, includes one calculation of the form factor, and the black line is if the form factor was 1, so if we were fully coherent. And here we see that for coherent, we are already slightly off. Yeah, and any deviation of this n-square dependence would hint to new physics. Okay. So let's come to reactor neutrinos. So reactor CEvNS. So here you see again an expected CEvNS spectrum. For a neutrino flux 40 meters away from a 4 gigawatt power reactor. We see different targets. So here the green and the blue line is are targets that contain tungsten, so something very heavy. Then a medium-sized target, germanium, and an orange, so the dashed orange line is sapphire, so something very light. So the overall normalization here depends, of course, on the neutrino flux. So if you go closer to your reactor, then you have a higher neutrino flux and the thing moves up. But what I want to draw your attention to is the x-axis. So here, before we saw KeV energies, and now we are at electron volt. Okay, so here the upper part is 1 keV here. And the spectrum falls even steeper than what we saw before. So, and the CEvNS spectrum has to always be compared to the backgrounds. So the gray area represents a background of 100 counts per kV kilogram days. And this is something that we can typically achieve in a shallow underground lab. So I get 10 meters of water equivalent, 50 meters of water equivalent. Yeah, so for reactor neutrinos, we need an even lower threshold, we need an even lower background, and we need high neutrino fluxes. So this table summarizes most of the reactor experiments. So for a complete list, I would refer you to this paper. So this is actually the Snowmass white paper on CEvNS. And unfortunately, so I have no time to go through all of them, but so for each experiment, I have a backup slide, so you can also have a look at them later. What I want to focus your attention on is that we have a lot of different detector technologies and also a lot of different targets that are being probed. There are many experiments that use high purity germanium detectors, and I will show an example for that in a minute. Those experiments, they reach typically an energy threshold of 1 keV. And then we have another experiment, the CONI experiment, that uses CCDs. So it's again a semiconductor, this time silicon. And we have detectors that read out scintillation light. So that is the neon experiment that operates sodium iodine scintillation crystals, and the red experiment that operates a liquid xenon TPC. Okay, so let me start with the CONUS experiment. It uses commercial P-type point contact high purity germanium detectors. So it's a diode reading out ionization. Those are, so each of the detectors has 1 kilogram, and they use 4, which you can see here in the vacuum capacity. They reach a threshold of about 300 electron volt, and those detectors, they're embedded in a multi-layer shielding consisting of polyethylene and lead, and very efficient neon metal. The detector is located at the Brockdorf power plant in Germany. They took physics data until the end of last year. Then the reactor was shut down. And since the beginning of this year, they are taking a high statistic background. They made a great job with their shielding. So they have a very low background. So here you see the background spectrum. Here you have an X-ray line that they use for calibration. And so the background they achieved is 11 counts per kilogram days in the energy region from 0.4 to 1 keV. That corresponds to 20 counts per kV kilogram days, as I showed on the previous slide, so on some slides before. So that means they reduced the background by a factor of 5 with respect to those 100 counts per kV kilogram days. In their data, they do not see an excess of CEvNS events. So they set an upper limit on CEvNS, which is 17, which is a factor of 17 above the standard model prediction. Nevertheless, so though they don't see CEvNS, they can constrain certain beyond the standard model physics scenarios. So scenarios in which the CEvNS cross-section would be enhanced. And that is, for example, scalar mediators. But they have a lot of results. And so I invite you to read this paper, which is very nice on this beyond the standard model physics searches. So the next experiment that I want to highlight is the CONI experiment. They use charged coupled devices. and they reach a very low threshold, so a lower threshold of 300 electron volt. So here you see a picture of such a CCD. It's also how cameras work. So in principle, they take a picture, and based on that, they can do particle discrimination. Also, so they're also running, and they haven't seen CEvNS so far. So their latest results, their latest limits is 34, is the factor of 34 above the standard model prediction. And so currently they're preparing an upgrade. Okay, so let me summarize what I just said and add something. So here you see again the fluxed average cross section as a function of the neutron number. Now with different contributions. So again in green we see the results from the coherent experiment for cesium iodine and argon. Yeah, so the future detectors, sodium and germanium. And below that, so the xenon experiment also looked at CEvNS of boron-8 solar neutrinos, and they set a limit. So here in magenta or pink, we see the flux average cross section expected for boron-8 solar neutrinos, measured on argon and xenon. And in red, we see what we would expect for reactor neutrinos. So here we have results on germanium and silicon. And yeah, the two limits that are being set. Actually, for germanium, there are 3 experiments that published the limits. That is, in addition to Konos, that's the Newton experiment, and then there are also results from the Dresden experiment. Okay. But of course, it's not that simple, and since I promised to also talk a little bit about the challenges, I have to mention that experiments using germanium and silicon, they suffer from quenching and the resulting uncertainties. So I'd like to explain briefly what that means. So here you see a sketch of a germanium detector as used by the Konos experiment. Then if you have a CEvNS interaction, you produce a nuclear recoil. And this nuclear recoil then produces lattice vibrations, so phonons, and ionization. And so the ionization, so the produced charges is what we read out. So the charges are then drifted to the electrodes, and this gives our signal. The phonons, so the majority of the signal which is produced, is not read out. And so that means, so a nuclear recoil of 1 keV produces a much smaller signal than, for example, a 1 keV X-ray that deposits its energy in the detector. And that means the nuclear recoil signal is quenched with respect to the electronic recoil signal. And the ratio between the energy deposited in the electronic recoil and the nuclear recoil is called the quenching factor. And there is one very successful model. It's called the Lintard model that many people use, and yeah, it uses a parametrization. Yeah, that is represented here by this K parameter. So the quenching is shown here. So here we see the electronic recoil as a function of the nuclear recoil. So if you have a detector with a threshold of 250 electron volts, electronic recoil. So because we typically use gamma or X-ray sources to determine the energy scale. So we have a threshold of 250 electron volt electronic recoil, then your nuclear recoil is either, so if you have a high quenching, then your nuclear recoil is below this threshold, it's just at the threshold, or it is above the threshold if you have very few quenching. That means that any CEvNS results highly depends on this quenching, and we need to really precisely measure it in order to know how many CEvNS events we do expect. So how many CEvNS events are above our detected threshold. And so the initial results of CONUS, they were presented with this plot. So you see the CEvNS rate as a function of this K parameter of the Lindheim model. And in red, you see the number of expected CEvNS events. So the smaller K is, the larger the quenching. And there is a lot of discussion about these quenching factors. So the CONUS experiment, they did their own measurement of this quenching factor. And yeah, so their results indicates that there is actually a lot of quenching. So the K parameter is quite small. So just to give you a number, so here, so with this quenching factor, it means that they would expect 5 CEvNS events in their data, and their limit is around 85. Okay, so much about quenching. Now we can ask, okay, so what should we do next? So how can we improve to really measure reactor, so CEvNS of reactor neutrinos? So first of all, we can start to improve the signal to background ratio. Sorry, there's a typo. So meaning we scale up the mass, we reduce the background, and we simply get a higher neutrino flux. But we should also work on our technology to measure the spectrum. So we should go lower in the threshold. So for example, silica, so the Connie experiment, they are going now to skipper CCDs, which is essentially the same, but they change the readout such that they can lower the thresholds by a factor of 3 to 4. But it's still a measurement of the ionization signal. So we lose a lot of signal. And then to really go to very low energies, we should measure the phonon signal instead of ionization or scintillation light. And here we have to go to cryogenic detectors. And so this will be, the rest of my talk will focus on cryogenic detectors. So cryogenic detectors is very simplified. We have an absorber crystal that is weakly linked to a thermal bath capped at a few tens of millikelvin. Now, so if we have, for example, CEvNS event, so we produce lattice vibration, or let's say a temperature increase in the crystal that we can read out with a very sensitive thermometer. So we are reading out phonons, which are very low energy quanta, meaning that we can achieve extremely low thresholds. So of the order of tens of electron volts, nuclear recoil, because we are reading out the full recoil energy. And this nearly independent of the particle type. So meaning that at least at high energies, so the nuclear recoil, so a nuclear recoil can be calibrated with an electronic recoil source such as X-rays. And as absorber material, we can use a lot of different target crystals, which is very nice if we want to probe this n-square dependence of CEvNS. And cryogenic detectors are already widely used in the search for light dark matter. So there's a large overlap because these detectors can easily reach very low thresholds and also get a very low background. And yeah, so the nucleus experiment is based on the CREST technology. So let me explain the nucleus experiment a little bit more because I'm working on it, so you're a little biased. So the nucleus experiment will be located at the Shore nuclear power plant, which is well known for the double Shore experiment, for example. So it's very powerful. So there are two very powerful reactors. And we will be located about 72 and 102 meters away from these reactors, but still have a quite high flux of 2 times 10 to the 12 neutrinos per square second per square centimeter second. So currently we are constructing the experiments here at TUM, and we will start commissioning of the different parts also here at TUM next year. We demonstrated that with our detectors, we can reach a threshold of 20 electron volts. And so here in this plot, you see the differential CEvNS rate for the two targets that we will use. In blue, calcium tungstate, where we expect to measure CEvNS with, and then a lighter target, sapphire, here shown in red, where we will do an essential background only measurement, which we can then use to constrain our background model such that we can increase our sensitivity to CEvNS. That is because, I mean, it's very unlikely that both reactors will be shut down at the same time. And yeah, so we get similar contributions. So we cannot do this typical reactor on, reactor off comparison. Then very briefly on the nucleus experiments. So we will use in total 9 calcium tungstate and 9 sapphire crystals using a tungsten transition etch sensor that was developed by the CREST experiment. So the 9 calcium tungstate, they add up, crystals add up to a total mass of 6 grams. Here you see our sapphire prototype that reached this 20 electron volt nuclear recoil threshold. So they're really tiny. So they have an edge length of 5 millimeters only. And then these detectors are, so they are mounted in a holder, which itself is instrumented to reject surface background and holder related events. And then the detectors are surrounded by a germanium cryogenic veto to reject ambient neutrons and gammas. And those detectors are then placed in the lower part of our dilution refrigerator, which provides the base temperature of 10 millikelvin. We also have multi-layer shielding. So from the inside to the outside, we have boron carbide and borate polyethylene to moderate and capture neutrons. Then we have lead to attenuate external gamma backgrounds, and we have a very efficient muon veto as the outermost layer because we're located basically at surface. So we have a lot of muons there that we have to reject. In order to understand if we can reach our background goal of 100 counts per kV kilogram days, we did an extensive Monte Carlo study, including the full detector geometry and all the vetoes. And so the Monte Carlo simulation shows that we can reach our background goal. And here you see a split up of the estimated rate in our region of interest from 10 to 100 electron volt, which will be dominated by CEvNS events. So this looks, I think, very promising. And so with that, here you see the CEvNS signal significance versus lifetime. So if we have a background of 100 counts per kg days, then we should see CEvNS within a month. The nucleus experiment, as I showed you before, will be eventually limited by statistics. So we can measure CEvNS on tungsten with a precision of 10%, and that's what we expect. But we can also search for, if we do that, we can also search for beyond the standard model physics, such as new couplings of neutrinos to quarks. So this sounds all kind of simple, but I mean, we have to be honest and say, okay, so our region of interest is 10 to 100 electron volt, which is really a new energy regime. And we want to do physics there, potentially also see new physics. So we have to understand this energy range very, very well. And here come the main challenges. So it's a new energy regime. So actually that might also bring some new backgrounds. And there is, so we think that there are new backgrounds. So there are a lot of dark matter experiments and also CEvNS experiments that see an excess of events below 200 electron volt. And it's so far unclear where this background should come from. And it is actually limiting dark matter experiments already. So in the past 2 years, there was a series of workshops dedicated to understanding this background. And yeah, so it's a very interesting series of workshops. So the next one will be a satellite workshop at TUM. So that is one part of the story. So the background in this very new energy regime. Then the other thing is we have no calibration sources below 1 keV. And this, especially the problem are calibration sources for nuclear recoils in this energy regime. But I mean, if we want to do physics, we need to understand our this energy scale, so the detector response of nuclear recoils in this regime. So I already talked a lot about quenching factors, and this is very well related to this. So let me try to explain you why. So quenching factors they are very important if you measure at higher energy, so 1 keV nuclear recoil, for example, and if you measure only the ionization or the scintillation signal. Now, why is it also so it's not the quenching factor itself that is important for phonon detectors, but it's the understanding of the energy dissipation in the detector that is important if you read out the phonon signal. So let me try to explain why. So here on this slide, so we see, let's say, a sketch of the energy dissipation at energies of keV. So there we think that we well understand the process. So if you have a nuclear recoil, then this is energetic enough to induce secondary recoils and to produce high energy electrons. This is all described by the Lindhard model, so how much electrons are produced and how much lattice vibrations. But then if we go lower and lower in energy, we have two effects, probably more. So one effect is that whenever you kick out a nucleus from its lattice location, this nucleus, I mean, it goes through the lattice and loses its kinetic energy, and then just stops somewhere, creating a lattice defect, which stores some energy, which still can be as low as a few electron volts. So you have that effect at all energies, but if you go lower and lower in energy, this contribution of lost energy in these lattice defects becomes comparable to your initial energy deposition. And there might be something even more severe. So at some point you hit the lattice displacement threshold. That means you do not produce secondary recoils, but you are left in this no secondary recoils, and also you stop to produce high energy electrons. So you are left at some point in this phonon only limit. And of course, this cannot be calibrated with an electronic recoil calibration, so with X-rays. So we don't know how big this effect is. We don't know if, for example, the direction of the nuclear recoil plays a role here. So we need to measure it. And therefore we need a direct and model independent way to calibrate nuclear recoils. And so here comes a new experiment that we just proposed. It's called CRAB, which stands for Calibrated Recoils for Accurate Bolometry. The idea is you have, so you capture a thermal neutron, and then you produce a compound nucleus, which is left in an excited state. So the excitation energy here is typically a few MeV. Then this nucleus de-excites, typically by emitting gamma rays or conversion electrons. But the interesting case is if the de-excitation occurs via the emission of a single gamma, and since this gamma has a few MeV, the nuclear recoil that this nucleus gets is of the order of 100 electron volt. Now, if this happens in your detector and the emitted gamma ray leaves the detector without depositing energy, then you are left with a pure nuclear recoil. And this is the signal we are looking for. So the idea of this experiment is to go to the research reactor in Vienna that can provide a very clean beam of thermal neutrons, which we use to calibrate a calcium tungstate detector. So here you see a simulated spectrum for a nucleus like calcium tungstate detector. And you see that we expect a clear peak at 112 electron volts and at 160 electron volts. Plus this feature here. So this would be a real breakthrough to have to measure such a spectrum and to really see that we can calibrate our detectors at this 100 electron volts regime. Okay, and here is the timeline for this experiment. So we actually did a proof of principle measurements over summer, and we're preparing a preparation on that. So we calibrated a calcium tungstate detector with a portable neutron source. Oh, I hope that we can put the publication online in a couple of days, so stay tuned. And then next year in 2023, we want to start building the experiment in Vienna, and then start calibrating calcium tungstate and sapphire detectors. Then the next step would be to upgrade this experiment with a gamma tiling. So since we're looking for those nuclear recoils which are induced by the emission of a gamma ray, if we can tag these gamma rays, we can really select even more lines very clearly. And yeah, we can push down the calibration lines to below 100 electron volt. Then we can also use this method to calibrate germanium. However, so germanium is lighter than calcium tungstate. So the induced nuclear recoils are also at higher energies. Nevertheless, this would be a real breakthrough to measure this clean nuclear recoil signal at 400 electron volts, and then also measure finally quenching factors with this measurement. Okay, so I hope I could convince you that CEvNS provides a very rich physics program. So there are many experiments running, many others are being prepared. There are also a lot of new ideas, and yeah, we hope that soon we can do precision measurements of CEvNS. However, there are still a lot of challenges ahead of us. So it's the low energy excess, so the background, it's the calibration and the understanding of the sub-keV energy range. There are still some discussion about the quenching factors for germanium and silicon. And then, I mean, since we want to do a precision measurement and we want to scale up the detector mass, this will be the next challenge, I guess. So especially for cryogenic detectors, this is not straightforward. But all these challenges are also found in dark matter and neutrinos double beta decay searches. So there's a large overlap. And so if you're interested in CEvNS, then I invite you to join us in March next year for the Magnificent CEvNS that we are organizing in Munich. So thank you very much for your attention.
Thank you very much. Yeah, that was very fascinating, very comprehensive overview. Do we have some questions from the audience? Bruce?
Yes, sorry, I'm not meaning to look at you sideways, Victoria. Thank you very much for the talk, which was very clear. Could I just follow up something on slide 28 where you were showing the sensitivity of coherent?
That is nucleus.
Sorry, of nucleus. So could, just looking on the right-hand side here, so do I understand correctly that this sort of orange band is the sensitivity of nucleus? Is that right?
No, it's so the orange band is on sapphire.
Yep.
And
sorry, from this legend here. Okay.
Yes, it's on sapphire because so for the regions outside, the cross section would be enhanced. Mm-hmm. So even though you have no measure on the CEvNS cross section on sapphire, you can constrain it. Mm-hmm. Then okay, it's very hard to see. Then green is on calcium tungstate. So here you have measurements.
See the green
small bands, and then if you combine that, you get the blue one. But yeah, it's
okay. So really, the most of the sensitivity comes from the calcium tungstate.
Yes.
All right, and the black point is the no non-standard interactions point here.
Yes.
What is this other black point here?
So the other black point is, so if you combine, so okay, maybe so you can always construct a scenario in which the contribution of the new interactions are twice as large as the standard model, as what you expect in the standard model. but
It's a
with the
negative
opposite
interference
sign.
point.
So yes, so they,
Okay, so that's, I see. And so it's accidental that the combined line goes, oh, I see, and that's why there are two bands from the combined.
yes.
Okay.
Yeah. So you always get two bands because you cannot distinguish those two cases. But and you get the band because, I mean, so okay, sorry, I don't know how to explain that very well. So you always get the two bands, but then you always get those two scenarios. So the standard model and the so the standard model where you reproduce the standard model case and the case where you reproduce twice the standard model.
Thank you. That's now clear. I hadn't understood the multiple bands or the 2 points,
Okay.
and now I do. I believe I do. And the dark shaded is the monojet, and the light shaded is charm. Is that right?
Yes.
Okay.
Yes.
All right. So between, and then the coherent 2017 is, what is coherent 2017 result?
In this band,
You've got coherent 2017 listed.
I think it's here. It's very hidden. I think there's a dark green, and is it a light green for the coherent?
Yeah, it's slightly tilted with respect to
it's somewhere underneath. It's somewhere
cosine.
underneath the nucleus projection.
Yes.
Okay. I'm sorry that took so long, but thank you. That's
No. I agree. It's a very hard plot, and I would have chosen the colors maybe a bit differently.
But it means that in combination with the LHC results, there will then be extremely strong constraints on these couplings.
Yes, and then also because the slope of these bands depends on the combination of protons and neutrons. So you also want to measure different targets.
Yeah, if you use a target with a very different end to P ratio, then potentially you could.
Yes.
You could cut down even further. Although that would have to be beyond the one shown here, because the sensitivity is entirely driven by the calcium tungstenate.
Yes, exactly.
Thank you very much.
Mikhail?
Thanks for the nice talk. Can I just ask one follow-up question to that plot? About those LHC monojet searches. Yeah, I know that's not what you're working on, but in case you know, do you know what kind of, well, technically they use probably effective field theory to extract those limits. How robust are those limits in those? So I'm just wondering whether we can fully trust that ellipse or not.
I have to say I don't.
Yeah, no, that's fine. But I have actually another question, which is actually more related to. Can you go to slide 21?
Yep.
So there was basically the number of CEvNS events versus that parameter from that quenching theory, from modified Linhart theory. And if I look at the blue curve, I would have naively expected it should be more like, I don't expect why it's going up there around that, why it's not just monotonously going down to lower values if I go to smaller case. I don't understand why it's going up there around that point, whatever, 0.162, where the purple line is. Do you have an idea what could that be? Because technically you just decrease, or you basically say how much is quenched and how much you actually see in the signals. So I would naively assume I should basically, the number of events which I should see should scale in a similar way.
Yes, but maybe one has to go really back to the statistics and see if they're already sensitive to some fluctuations here.
Mm-hmm. Okay, good. Yeah, no worries. Thanks.
Anyone else?
Yeah, I've got one question.
Yeah, go, Jay.
Have you considered in your gamma ray calibration, did you do any calculation to see if you would expect any Migdal events?
No, for us in nucleus.
Yeah,
No.
like just for the calibration. It's just I thought of doing this, but it didn't work very well for xenon that we were thinking about. Anyway, it could be something cool because like when you're doing a low energy recoil calibration, nuclear recoil calibration, if you get any Migdals, it's going to be included in your calibration. So that's like, it's kind of good. I'd just be interested if with the flux that you're using, whether you'll see any.
No, I honestly have to think about if that was possible with a calcium tungstate detector. And what this would mean as a calibration signal in our phonon detector.
Yeah, right.
It's an interesting part. It's an interesting question, but no, we haven't.
Okay, thanks.
So maybe I can go next. So you're talking about wanting to do sort of precision measurements, but one thing I have no idea about is how well do you know the flux, like the reactor flux? Is this something that is known so well that you can really do the sort of precision measurements that you're claiming, or because how else would you know it without measuring these events down at such low energies?
Yeah, so above the IBD threshold, so above 1.8 MeV, the flux is known to 2-3%, I would say. So let's say if we scale up nucleus by up to a mass of 1 kilogram, we will hit this uncertainty, definitely. So that means, yeah, so let's say if the reactor flux stays like, so if the uncertainty on the reactor flux stays like that, we will hit these 3%, or we will be dominated by these 3%. There is an effort ongoing also in nucleus to get a more precise neutrino flux prediction, especially because below the IBD threshold, so below 1.8 MeV, the flux is rather unknown, let's say it like that. And their uncertainties are more like 10%. However, the majority of neutrinos that we are measuring lies above those 1.2 MeV. It's rather 3 MeV, let's say, the typical neutrino that we measure. But it's certainly a very good point, because also if we go to, so for the upscaling, the target will probably not be calcium tungstate, because I mean we have homemade crystals that we use, and then it would be easier to go to something like germanium or silicon, and then of course we would also probably see more of the neutrinos below the IBD threshold. And yeah, so colleagues of us are working on it to get also a more precise description of that flux, down to something that is compatible to the flux above. And yeah, I mean, we're not the only experiment, so yeah, I think there's a large interest in the whole community to understand better the reactive flux. There are many projects ongoing.
And I might just ask one sort of more broad question. I mean, there are several of these sort of smaller scale experiments, and you're trying to do you're trying to push towards, you know, a precision measurement of sevens, and, you know, searching for BSM physics, nuclear physics, and all of this. Is there an obvious sort of end goal that all of these experiments would be working towards, or like a point of convergence, perhaps? Like, you know, the dark matter community, there's kind of obvious directions, like they want to get to a neutrino floor or something like this, or they want to get to some SUSY model. Is there like some point on the horizon where this sort of field would be moving towards?
Yeah, I mean, I think one goal is to really do a precision measurement of the sevens cross section of a few percent. Okay, I'm not sure that's really a precision measurement, but let's say for us now, a few percent would be really good. Then, I mean, one goal is really, so now we're showing all these models of the beyond the standard model. So personally, I would also find it very great if we could push, for example, the germanium detectors also down to lower energies, and then look for neutrino magnetic moments. I mean, this is certainly one goal, to do that with sevens, but there you need really low thresholds, yeah, medium size target such as germanium, I think, is more favorable for something like that. But I'm not sure that there is a real measure to say, okay, now we go towards this, because yeah, this precision measurement, and I mean, there you need to scale up the mass, and this is very difficult. First of all, then you want to go lower in energy, such that you're also sensitive to, for example, neutrino magnetic moments. And as I said, there are so many challenges. So I think first the community should try to understand all these, or tackle all these challenges, and yeah, then also before we say, okay, where we stop, because I think there's a lot of potential still in this measurement, and we're quite far from reaching really our goals to do this precision measurement with reactor neutrinos. And then I think I mean, we also want to measure a lot of different isotopes. That is, of course, to disentangle some of the degeneracies, for example, in the plot that we discussed before on the new neutrino couplings, but also to do this precision measurement. And then, I mean, let's say once we know what the sevens cross section is, we can start to use it to measure astrophysical neutrinos, for example. So there are many ideas, or there are a few ideas how to measure, for example, supernova neutrinos with a LED, so scattering on LED. There's the Resnova experiment, but also all the dark matter experiments. They have the same goal, so they want to go higher in mass, so higher in exposure, measure lower and lower WIMP cross sections, and that makes them really good solar neutrino detectors, or also atmospheric neutrino detectors. So I think there's a lot of potential, but still also a lot of work to do before this can be done.
Okay, so last chance for anyone to ask a question before you finish. But if not, I think we can probably close it there then.